Hey, hi everyone. My topic today is Node2vec. It's a scalable feature learning network implemented by Aditya Grover and your S3W2 at Stanford University. And Node2vec is an algorithmic framework for learning continuous feature representations for nodes and networks. So as you can see, the nodes are clustered based on its connectivity. So it's a mapping of nodes to a low-dimensional space of features that maximizes the likelihood of preserving network neighbors of nodes. I'll explain this in detail from the rest of the slides. And it's semi-supervised algorithm in a way how it can train with 10% of data and actually predict the rest of the network. And it uses a stochastic gradient descent and uses a model from skipgram. So instead of words, it uses the connectivity patterns in network. And it uses a random walk, second order random walk approach to generate the samples. This part is similar to deep walk in how generating embeddings from the random walks. However, in Node2vec, it adds a controllable vector in generating random walks. So when it comes to deep learning or machine learning in network analysis, it's difficult to take the network's raw representation and use it right away to build a model. So it's commonly used to extract a representation of each node's features to train a model. So previously, there has been algorithms such as PageRank, which creates the features based on the degree. And there's also matrix factorization, such as spectral clustering. However, the paper mentions that it does not scale to real-world networks. And there's also deep learning methods, however, is known to have a really high cost training time. So currently in Node2vec, the authors created a mapping F so that any map's node can be projected as a vector format in a d-dimensional subspace. So it's basically embedding nodes with similar network neighbors closer in the feature space. And this is done by maximum likelihood optimization, objective function that uses random walk procedures, which saves space and time complexity. So the authors also mentioned that this paper is different from the other previous works and how it has a flexible notion of neighborhoods. So commonly when it comes to random walks, there are two types of search strategies, BFS and DFS. So BFS is a breadth first search. For example, if we start from node over here, the search only extends to the nearby networks. So for example, S1, S2, and S3, S4. So it's more local and known to have a characteristic of homophily in how it collects the characteristic from nearby neighborhoods. However, for DFS, depth first search, if you start from node U, it begins to search to S4, S5, S6. It goes quite deeper when searching randomly. So in this case, it's more global compared to BFS. And if you look at the subgraph, if we divide the whole graph into two, you can see how node U and S6 have a sort of a structural equivalence in the positioning wise. So that's the characteristic of DFS. And both of them, each of them captures the microscopic and macroscopic view of the network. So this is quite important in real life cases. Let's say we have a social network of bloggers. So some bloggers may interact with each other a lot. In that case, we can see a homophily characteristic between the bloggers. However, there might be familiar strangers. One person who does not interact with a group of people, however, that person may promote the same product, talk about the same services, and yeah, they may not interact but share same interests, thus structurally equivalent, such as U and S6. So these two are commonly used search methods. However, being skewed to one cannot really capture real life network. So in this paper, the authors try to set a search bias alpha, which kind of controls between the scope of BFS and DFS. So if you look at the graph over here and the equation of search bias alpha, and let's say the search started from T over here and have moved on to V. And now at the node V, the search has to determine whether to go back or to go to X1, X2, or X3. However, in this second order random walk, so rather than just random walk, second order means it takes account of the previous node as well. So if the distance from the previous node is 0, indicating if the V was to go to T, was to go back to T, since the distance is 0, the search bias is set as 1 over P. And if V was about to go to X1, since the distance between T and X1 is 1, the dtx is 1, so the alpha is set as 1. However, X2 and X3, they're 2 steps away from T. Therefore, a search parameter 1 over Q is set. And to explain what P and Q is, the authors set the parameter P so that it will control the likelihood of going back to the previous node. So if the P value is big, one second. If the P value is big, it's less likely to go back to a node that's already visited. However, in reverse, it will lead the walk to backtrack a step. However, on the other hand, the input parameter Q, it tries to determine whether the search should go inward or outward. So if it has a high value, the walk tend to go to the node that's close to T. However, the opposite, the walk is inclined to visit nodes farther away from node T. So these two parameters, P and Q, can be hypertuned while using the model. And using these sampled random walks, the feature is learned using skipgram architecture. In skipgram, if we have interval of 2, we're gonna extract words like this. So we're gonna have pairs I eat and eat lunch. And if we have much more sentences like this, the deep learning structure assume these are edges and other nodes in deep learning network. We're gonna set each of the words, I ate lunch, and many other words. We're gonna train by using one-hot encoding, and this way, when a new sentence comes in, I am hungry. If word N comes in, on the label side, the probability of I and hungry should appear to be higher than the other words. So it works in the same way for Node2vec. However, notice we have used random walks to collect the different nodes. So if the node have traveled from A, B, C, D, This is also fragmented, whether we call the L value over here, whether the L value is 3 or 2. Each of these are segmented and input to the deep learning network. And the space over here is called as the low dimensional feature space in this paper. So this is how the Node2vec uses skip-gram architecture to train the connectivity patterns in a network. And in the end, the maximum likelihood is used to predict the likelihood of different nodes having probability of being next to the current node. And here some assumptions are made, such as conditional independence between the different likelihoods, thus this notation over here. And it's also assumed that the pairs of nodes have symmetry in feature space. So node A to B and B to A should have similar feature space, same feature space. And these two equations and this equation over here is simplified to the final equation. And yep, according to the skip-gram architecture and stochastic gradient descent, the network is trained. So the summary pseudocode is like this. Basically, it uses random walks called Node2vec walk in order to collect the samples. And there's a pre-processing step. And finally, stochastic gradient descent is used to find the feature space characteristics. So the paper has gone through several experiments. First one is Les Miserables network. And if you look at the diagram over here, on the top part, the P and Q values are adjusted so that the network would learn local neighbor BFS or local characteristics first. So if you look at over here, the nodes are clustered so that the neighborhoods are in close proximity to each other. However, P and Q values are controlled differently on the bottom part over here. So it's more focused on DFS, structural equivalence. So if you look at the diagram, the colored nodes are dependent on more how it's structured based on the center nodes. So testing on this network, the authors mentioned that this Node2vec analysis, Node2vec model can be applied to real life situations, which go through both BFS and DFS importances. And another experiment that was done was by running Node2vec against different multi-label classification models, such as spectral clustering, deep walk, and line. So the data sets were set differently, such as blog catalog, using the interactivity between different bloggers, protein-protein index. It uses a gene sequence to determine which are more interactive with another, and also Wikipedia. And here, word co-occurrences are used to create a network. And as you can see, the macro F1 scores over here, the Node2vec has performed the best compared to the other ones. And deepwalk actually performed second. And this is also the same experiment. However, the training data over here, they were given 50% of the nodes. However, we can see how it performed based on the percentage of nodes. So 20%, 40%, 60, 80, and 100. And from all of the graphs, we have the macro F1 score and micro F1 score, micro and macro, sorry. And you can see that Node2vec has performed the best in all of the scores and different data sets. There was also a perturbation analysis done. Since real-world networks, they do not always have all the information, since some of them have missing edges and some of them have noisy edges. Those were experimented by taking off some of the fraction of missing edges and actually adding additional edges so that the network would seem more noisy. And both of them, according to the author, the F1 score did not too much compared to the state-of-the-art models. And scalability-wise, they have started from 100 samples to 1,000,000 nodes. And even with million nodes, the model has performed less than 4 hours. The scalability-wise, Node2vec performs the best compared to the state-of-the-art models. And there's also a link prediction analysis where some of the edges were removed and tried to be replaced or predicted with the model. And here you can also see Node2vec performing the best. The scores were measured with AUC, and you can see DeepWork also performed very well. However, Node2vec has the best scores compared to the other ones. So to conclude this presentation, I want to re-emphasize how Node2vec can explain both exploration and exploration trade-off by having a controllable factor such as P and Q. And the authors mentioned that they would like to look further into continuous feature representations. So I was watching one of the YouTube videos, the authors explaining about Node2vec, and they were looking forward to implementing a graph that was growing, since real-life applications can differ every time. And he was talking about training the local parts of the newly formed network and then connecting that with the original training data set to reduce the complexity. So I'm very looking forward to the other papers this author has published. And that's it for my presentation today. Thank you.